taking necessary sufficient condition for differentiability. It is very important. You should remember that when function is differentiable at point AB, it should be always exist. Important part is that partial derivative of function with respect to x should exist. Partial derivative of function with respect to y at AB should exist. Then we can apply necessary condition for differentiability. We are stating here necessary condition for differentiability is that here it is given statement, let f be a real valued function, f be a real valued function which is defined on a neighborhood of point AB. The point AB is there, which is in region, which is in given region. At that point, function is defined at that point AB, in the neighborhood of AB, and that function f is differentiable. Function is differentiable at point AB. Then, if f is function which is differentiable at point AB, then it is necessary that f should be continuous at point AB, and first partial derivative with respect to x at point AB, partial derivative of function y at point AB, both should be exist. That means function is said to be differentiable. Necessary condition for differentiability is that function should be continuous at AB, and both partial derivatives with respect to x and with respect to y should exist, or both are existing. Okay. For that purpose, we are proving this. Just we are already discussed when function is differentiable. Function is differentiable if in the neighborhood of point AB, a plus h, b plus k is a point, and we are taking by this way f of a plus h, b plus k minus difference between f of a plus h, b plus k minus ab should be equal to a into h plus b into k plus h into phi of hk plus k into psi of hk. Here a is partial derivative function with respect to x, b is partial derivative function with respect to y, h is small increment, k is also small, h is small increment in x, k is small increment in y, h into phi of hk plus k into psi of hk. Here this phi and psi, which are functions such that they are tending towards 0 when h and k tends to 0, and a and b are constant numbers. That means these are partial derivatives with respect to x at point AB, b is partial derivative function with respect to y at point AB. Okay, then it is equation number 1. It is taken to be as equation number 1. Now, up to this you are known. Up to this you are known all these terms or these terminologies. Function which is differentiable. Then, according to definition of differentiability, we are writing equation number 1. After writing equation number 1, case number 1. Here in this case, we are taking k is equal to 0 in equation number 1. What will happen? See. Taking limit as hk tends to 0, 0. In equation number 1, taking limit as hk tends to 0, 0. What will happen? As hk tends to 0, 0, phi and psi tends to 0. And taking limit here from equation number 1, limit as hk tends to 0, 0, f of a plus h, b plus k minus f of ab, which is equal to on right hand side, limit as hk tends to 0, 0 of this bracketed quantity a into h plus b into k plus h into phi of hk plus k into psi of hk. You are already familiar with that concept. A, here due to h tends to 0, this part will become 0. As k tends to 0, this part will become 0. H is 0, phi and psi, h and k both are 0. phi and psi tending towards 0, 0 as hk tends to 0, 0. Therefore, right hand side of equation, above equation will become directly 0. This part will be 0, and taking this f of ab on right hand side, this equation will be converted to new form. Limit as hk tends to 0, 0, f of a plus h b plus k, which is equal to f of ab. As function is continuous at any point, as definition of continuity, function in fx y is said to be continuous at point AB if limit as xy tends to AB, it should be f of AB. According to definition of continuity, you can see here limit as hk tends to 0, 0, f of a plus h b plus k is equal to f of AB, then function is said to be continuous at value of the limit should be equal to value of the function at point AB, then function is said to be continuous. Okay. First part is proved here. F should be continuous at point AB. First part is proved here. Function is continuous at AB. Now second part, we have to show that both partial derivatives are existing. We have to show that both partial derivatives are existing at point AB. For that purpose, case number 2. In equation number 1, we are taking k is equal to 0. Try to understand. In equation number 1, we are taking k is equal to 0. Therefore, this equation will become directly 0. This part of equation will become 0. Here k becomes 0. H remaining as it is. That means this equation will be converted to new form. Equation 1 takes the form f of a plus h comma b, because k is 0 minus f of ab on right hand side of equation 1, a into h remaining as it is, plus h into phi of h0, h into phi of h0. Here k is again 0. Now I am taking h common from this part, then what will happen here? Remaining term will be a plus phi into h0. H is taking common and dividing to left hand side. We are taking h common and dividing to left hand side and taking limit as h tends to 0. Three steps are doing directly. Above equation on right hand side, h is taken to be constant common and divide on left hand side, or dividing throughout by h to above equation. वरच्या इक्वेशनला जर आपण h ने डिवाइड केलं तर हा h कॅन्सल होईल आणि इथे डिवाइडेड बाय h होईल. That means we are dividing our equation by h and taking limit as h tends to 0. Again see it is while you are defining partial derivative with respect to x, while you are defining partial derivative with respect to x at point AB, which is equal to limit as h tends to 0, f of a plus h b minus f of ab divided by h. This is the definition of partial derivative of function at point AB. Same situation is there. Left hand side is partial derivative of function with respect to x at point AB, and on right hand side what will happen here? This phi will become 0 as h tends to 0. As h tends to 0, phi will become 0. This becomes 0, therefore there is only a. That means limit as h tends to 0, f of a plus h comma b minus f of ab divided by h, which is equal to a. But left hand side is partial derivative function with respect to x at point ab. Therefore fx at ab is equal to a. That means first partial derivative with respect to x is existing. Similar case, in case of above equation number 1, we are putting h is equal to 0. What will happen? See, we are putting similar case. While we are putting h is equal to 0, then what will be converted part of equation? This will be, we are putting k is equal to 0, then equation will be converted to f of a, it is h is equal to 0, b plus k minus f of AB, which is equal to on right hand side k, h is 0, therefore bk plus k into psi of hk. Here h will be again 0, therefore it is only k. Again you can take k common and dividing throughout by k, that is f of a b plus k minus f of ab divided by k. On right hand side it will be b plus psi 0 k. Okay. And now you are taking limit as k tends to 0. This will be our limit of this term. K tends to 0. What will happen on right hand side? This part will be directly 0 and there is only b, and it is partial derivative function with respect to y at point b. Therefore fy at ab is equal to b. Both partial derivatives are existing, function is continuous. Therefore the given conditions for differentiability, that is necessary condition, is satisfied. It follows that fxab, fyab is existing, function is continuous at ab, therefore it is differentiable at ab. Okay.